Yeah, so this is a work done with the collaborators from Himachal Pradesh University, Charu Diman student, PhD student, Raman Sharma, my collaborator. Okay, and this is basically related to the computation of resistivity using memory function formalism, which we developed here a decade ago. And so this problem was given to the student, and so the initial sort of plan was to calculate resistivity for a material, magnetic metal, near the critical point. For example, you take example of iron, and then if it is in a paramagnetic phase, near the critical point, near the Curie temperature, in the paramagnetic phase, there are going to be paramagnons. And what happens if the electrons scatter via paramagnon generation? What is the behavior of resistivity as a function of temperature in 3D metals? So that was the plan. Okay, so it progressed, but then suddenly it occurred to us that this problem can be also used to investigate what happens in the case of resistivity in cuprates with some additional assumptions of quantum criticality, which has been verified. Okay, and then we could observe that yes, this goes through, and we have sort of some correspondence with the people who work in the field, the leading authorities, and we are quite encouraged about it. We are quite enthusiastic about it, and let us see what happens at the end of the day. But to us, it appears that we have done something reasonably good, which should constitute the solution of the problem of linear resistivity of cuprates, which has been a very challenging problem. Okay, before I go to that, so what I did, I just planned the presentation in two parts. One, I'm going to give you the brief background in the electronic transport theories, and then second part is this real work which is related to the T-linear resistivity of cuprates. Okay, so for the background part, so okay, so this is the part which some decade ago in 2015. So I gave a course, advanced course on electronic transport theories. So it went very well, and then I sort of did quite a thorough study, and I published a book also. So it is taken from my book. But this is a very central topic in condensed matter physics. These models are discussed in various books. There are many books. For one, for example, is by electrons and phonons by Zeeman. Okay. So what I'm going to do is to tell you the main milestones in the theory of transport phenomena, electrical conductivity in metals, to be specific. Not going, definitely it's not possible, not going into the technical details of the formalism, only sort of stressing the basic assumptions and results. Okay, so very first theory was put forward by Paul Drude, okay, in the 1900, and so basically at that time it is a time when people started to understand thermodynamics in terms of atoms. So statistical mechanics was developed. So basically Maxwell was there, the Boltzmann was there. So they developed this statistical mechanical theory. So ideal gas equations were derived, Boyle's law, sort of all those ideal gas equations were derived by assuming that the gas consists of atoms or molecules, and these molecules in agitation at a final temperature, and then they strike with the wall of the piston, so they create pressure. Yeah, so basically then what happened, this man came, Paul Drude, so he just took that all the what is called kinetic theory approaches, Boltzmann kinetic theory methods, and applied to electrons in a metal. So he assumed that electrons are very much act like molecules or gas molecules, purely classical mechanics, because at the time no quantum mechanics was there. Okay, so then he assumed that electrons are charged particles. If the electric field is present, there will be a force on the electron, and then this is the Newton's law, but the electrons will collide with the ion cores. That is his fundamental assumption, that there are positive charges, okay, and then the electrons are negatively charged. The cathode ray experiments already showed, from J.J. Thomson's cathode ray experiments showed that electrons are negatively charged particles. So assume that these negatively charged particles scatter off the ion cores, and due to the scattering their momentum degrades. Okay, so this is some constant report there due to the scattering rate. And then if you do the steady state situation report equal to 0, you get P in terms of electric field, but then the P is also connected with the current density, number of electrons per unit volume times velocity, drift velocity basically, and the charge, minus sign because electrons are neutral charged particles. Okay, and then since you are in linear regime, the amount of current density is proportional to the applied electric field. The proportionality constant is conductivity. Okay, from this to these three equations, the DC part can be connected. If Et is some cosine omega t, then you can also get AC conductivity. So basically the AC conductivity is it is a complex function. It has iota sitting here, so it will have real part and it will have imaginary part. If you put omega equal to 0, you get DC conductivity. So basically DC conductivity is m square upon m times tau. Okay, so typically for simple metals like gold, the number of conduction electrons, it is conduction electrons, the electrons they conduct electricity, it is 10 to the power 27 per meter square. This is electron charge, 10 to the power minus 19 coulomb, mass of the electron 10 to the power minus 31, and the tau is in the femtosecond, so it comes about how much? In milliohms, I guess, right? Milliohm centimeter. So basically this is the one result, but the most relevant result, most crucial result which he obtained is the ratio of the thermal conductivity upon the electrical conductivity. So kinetic theory also the same. This result he took from the kinetic theory of gases, that the thermal conductivity of a gas or particles is given by 2/3 V square. CV is the heat capacity times the tau, the time between the collisions. Okay, and he took the ratio, he got this expression. So the ratio of the thermal conductivity to the electrical conductivity is proportional to temperature, and the proportionality constant is called Lorentz number. Okay, and actually this expression was already empirically derived by these men, Weidmann and friends. This was already known, and he saw that even the constant of proportionality, which is called the Lorentz number, it was also very good. So he was very happy that his theory is working, so that gave a lot of importance to this model. Actually, there is some element of truth in it, but we know that there was, you people know from the first course in solid state physics, he estimated velocity by using Cuprates theorem, which is 100 times less, and then the velocity the heat capacity is estimated to be 100 times more, something like that, because the heat capacity he assumed classical gas, but the electrons, you know, they are distributed like Fermi-Dirac distribution. Their heat capacity is very less because due to Fermi-Dirac distribution, most of the electrons are paired up, and only at the Fermi surface in the zone of width kBt, those electrons are thermally available. So the heat capacity is really less as per the classical value. So somehow some cancellation happened, the balancing cancellation happened, so he got good result. But later on it was known that he could not explain why the heat capacity, classically the heat capacity would be 3/2R, right? So if you take classical gas, electron as a in 3 dimensions, this is the degrees of this is the kinetic energy per electron multiplied by n is the total kinetic energy differentiated with respect to temperature. This is the heat capacity, 3/2 kBn. This is the heat capacity. This is a huge heat capacity, and it is never observed because electrons are not classical particles in metals. They form Fermi-Dirac distribution. Okay, so clearly the very deep flaw was there, but he just sort of it went under the rug. Actually, he could not notice it, and later on things became clear that heat capacity, this much heat capacity, nobody sees. Okay, but the biggest problem was that in metals, if you heat a metal, resistivity increases with temperature. Okay, and if you cool the metal, reverse, it decreases, and there is a characteristic law that the resistivity obeys. So at high temperature it is still linear, at low temperature resistivity goes at T to the power 5. Okay, so this is something which Drude theory cannot explain, because in the Drude theory the tau is just a constant. There is no temperature temperature appearing in this expression. So conductivity, inverse of conductivity is resistivity, rho is 1 by sigma. So there is no temperature sitting. So this entire graph was complete mystery to Drude. Okay. So then in 1926, when quantum mechanics was put in place by Heisenberg, Schrödinger, and others. So it was by Fermi. Basically, the Fermi. There is an article which has been translated from Italian to English by Fermi. So he argued that as you know, in atoms you can pair two electrons in one shell, in one orbital. So one electron upspin, another electron downspin. So he argued that that shell thing should also be applicable to electrons in metals. So metals have this k levels. Each k level will have one electron upspin, another electron downspin. So he came up with the Fermi-Dirac distribution. Okay. And that explained heat capacity should be very, very small, because now you know only near the Fermi surface very small number of electrons are available for thermal conduction. So that was the status of the field, and real progress happened in 1930s when Flex Bloch actually Bloch was a postdoc with Heisenberg. So Heisenberg gave this problem to Bloch. That what happens if you have electrons in a metal, so you have periodic potential, basically you have periodic potential, you put electrons, you solve Schrödinger equation for this problem. This was the problem given by Heisenberg to Bloch. So Flex Bloch solved it by Fourier analysis, and he saw that he obtained a couple of very novel results. Now he called theorems, Bloch theorems. First Bloch theorem is that the electrons are running waves, they are not particles. They run through the lattice. And so they are like plane waves, but this is a modulated plane wave. So the plane wave, there is a prefactor which is modulated plane wave that obeys the periodicity of the lattice. The modulated plane wave, the Bloch theorem. And then he noticed that there are bands. Right? There is a conduction band, there is a forbidden band, there is a valence band. So if the conduction band is full, the gap is large, it's insulator. So all those things fall in place immediately. Second problem he tackled was the resistivity problem. So what he did, he wrote the Boltzmann equation which was already there, and he applied the Boltzmann equation to electrons in metals. So what he did is, so he wrote the collision integral in such a way that, for example, here is this standard term. This is the del G by G is the non-equilibrium distribution function, and this is the drift term, the del G by del K dot F can be charge times the electric field. This is the collision integral. Collision integral has this transition probability. This is the rate WKK prime can be computed from Fermi golden rule. It gives the rate at which the electron in K prime state goes to K state, or vice versa, by generating a phonon, for example. And then this GK is the minus sign because this is a loss, and integral over K dash minus plus. So K dash is how many electrons scattered from K dash goes to K. This is the gain term, this is a positive term. So just gain minus loss, basically. And he solved this equation by using this. This is the diagrammatic representation. K goes to K prime, it generates a phonon, or K prime goes, the K goes to K prime, it can absorb a phonon with wave vector minus Q. The momentum must be conserved. And then he calculated, he solved the non-collinear distribution function, then he computed conductivity. Okay, and then he saw that yes, he obtained these results. It's the high temperature T linear, low temperature T to the power 5. So basically, this problem which Drude could not solve, it was solved with the advent of quantum mechanics, because the Bloch had this now clear understanding that it's not particles striking, it is actually waves actually, okay, scattering from one quantum state to another quantum state. Okay. So he could solve this problem. But there is a problem with the Bloch-Boltzmann theory also. So let us not go into this technical detail.
To understand this different behavior with respect to temperature and scattering wise, what physically has differentiated?
Yeah, this is a good question. So basically, okay, I can qualitatively tell you what is happening here. So you see, what is the resistivity? Is the number, the scattering, let's say. Yeah. So how many phonons are there in one mode Q? So number of phonons is given by 1 upon e raised to the power beta omega Q minus 1, right? The Planck distribution for phonons. Now at high temperature, okay, H bar is there. Now this H bar omega Q, so omega Q upon kBT. Now this Fresnel energy cannot be very large. It has a cutoff. That's called Debye cutoff. Okay. So let us say that this is much less than 1, even when this Q is QD. I mean the maximum possible Fresnel energy, some say 10 millielectron volt. Your cavity is much greater than that. That's the room temperature. Okay. So room temperature is 0.03 electron volt. 30 millielectron volt is the room temperature. Let's say this is 50 millielectron volt. So this is very small. So then if this is small, then you can Taylor expand it. Okay. So it will be e to the power. I mean, you Taylor expand it. It will be kVt upon that energy scale h bar by omega b. Right? It's proportional temperature. Right? I will Taylor expand it. 1 plus h bar beta omega q plus all of the terms minus 1. So I am neglecting the terms. So I have h bar omega q divided by kVt. kVt goes upstairs. So kVt upon h bar omega q. So this means that a high temperature number of phonons proportional to temperature. So this means number of scatterers are more as the temperature is larger. So that's why you are T linear. So you get T linear behavior at high temperature. But at low temperature, it's a little complicated. At the low temperature,
that's why I think the number of phonons are basically
yes. Low temperature of T cube behavior of heat capacity due to lattice vibrations. The heat capacity goes at T cube. So number of phonons goes at T cube. But why should be T to the power 5? Now, because at low temperature there is this, because electrons are fermions, they can't just scatter. They scatter if the state is available to scatter. So you have Fk multiplied by 1 minus Fk. It's called polyblocking. That is another T square factor comes into picture. So T square multiplied T cube. Very rough way of speaking, it gives T to the power 5. This is the polyblocking. The T5 signature shows that electron is a poly law. The poly principle is action. High temperature, the poly principle is not in action because your occupancy of the levels is much less than 1. So poly principle is not acting here, but the poly principle is acting here. Okay. But it has a problem actually. The problem is that the Holstein process cannot be explained. Let's leave it. It's a higher order process where even at zero temperature, there are no phonons. A photon can generate electron hole pair and then it can also generate a phonon. 3-body process. So that was not captured by Boltzmann equation. So we can leave it. Now the thing is that this simple looking Drude law here, this tau is seems to be completely a constant factor, but it turns out that this is not a constant actually. This is actually depends upon frequency and temperature. This is called generalized Drude scattering law. So how do you reach from this 1 by tau to 1 by tau omega t? That's a very beautiful chapter in non-equilibrium statistical mechanics. The one way to look into this is through following the logic of the Langevin equation. So let us treat the electron as a Brownian particle. So this is the mass of the electron, this is the velocity of the electron, a time derivative of that. Then there is a systematic part like in the Brownian particle. So Brownian motion happens when on one side of the Brownian particle lots of molecules, water molecules strike. Then there is imbalance of force. The Brownian particle dash in one direction, but as it dashes, it faces more molecules from the front side. Its field faces a drag. So fluctuations and drag. So they're the two sides of the same coin, the fluctuation and drag. So this is a drag, and this drag is very much like stochastic drag actually. The falling water droplet in atmosphere feels the drag which is proportional to velocity. This is the same drag. This is Stokes principle, the same drag. But at the same time, this drag must come in addition with this random force. This is RT. RT is a vector which has a random direction. And then RT and RT dash, they are not correlated. Okay, so they are not correlated. But then since the electron is a charged particle, you can have electric field acting on it. Okay, so then you can solve this Langevin equation by doing some Laplace transforms, and you get conductivity in terms of the mobility. Okay, and then the same Drude formula can be obtained from the Langevin equation. Okay, is another way to look at the Drude formula. You can use Langevin equation to drive it. Now, to see that there is a problem with the Drude formula obtained from the Langevin equation, let us look at the equation from which the Drude formula is derived. The equation is Langevin equation. Now it is known, very well known, okay, from the studies of non-equilibrium statistical mechanics. It's not a new result. It is known to people like Kubo, Van Kempen, all those things in 1950s, 60s, that this suffers from a very big defect. The defect is, if you look at the velocity correlation function, okay, so you take this, you solve the Langevin equation by some Fourier transforms, and then you reverse Fourier transform, take the expectation value, this is the ensemble average, then this is the law. Okay, at large time t, okay, this vanishes. That's sensible, because the correlation between the velocities must vanish if the time difference between them is large. But it has a problem. We should differentiate this with respect to time and put time equal to 0. It is not equal to 0. Okay, if you differentiate with respect to t and then put t equal to 0, it is not, this correlation is not equal to 0. So you can write this correlation as d by dt of this by factor of 2, half d by dt of this correlation. So the question is that the correlation, the derivative of the correlation should not depend on time, right? The time derivative of the correlation should not depend on time, because you are in a steady state situation. You are in a steady state situation. If it is transient, then yes, but you are in a steady state situation. It should not be 0, but it should be 0. This is like your translation of symmetry, right? And in a vacuum, your translation of symmetry. Here also there is a symmetry in time, although these things are fluctuating. But this is a translation of symmetry in time. Yeah.
The memory only is captured through the first systematic part, not the random part.
First systematic part, yeah.
It is only through this. The memory is captured. This is a correct.
Now we will come to the memory. It is memoryless at the moment. Here we have not put a memory. It's just some constant drag factor that is there. Okay, and so the particle is driven by the fluctuations, basically.
But it's actually keeping the information what happens something.
It's a Markovian. It doesn't remember. It's a Markovian. So the Brownian particle actually. So what happens that it doesn't remember. So the motion would look like if you take it. For example, it's very easily observable nowadays. I mean, you can have some microscope with some good optical microscope can work. The pollen in water, the pollen grain, if you look, it will have zigzag path. So each trajectory is completely independent from the previous trajectory. So there is no memory, basically. Okay, but yeah, I mean, if we go to a smaller time scale, okay, then things differ. I mean, this becomes non-Markovian process. Okay, and this is not true basically. Actually, to some extent, yeah, it can be true, but in general, this Markovian approximation of physical processes not always works. Okay, so one thing is that the stationarity problem with the Langevin equation. So there is a problem with the Langevin equation, and Dudet formula obtained from it is bound to be invalid. Okay. So then comes the generalized Langevin equation, which solves this problem of stationarity, because this theorem cannot be violated. Langevin equation violates the theorem, and that violation is exactly coming as you asked this question. That violation is coming because we are throwing away what happened to the particle just after the collision. Okay, so although it is random, but the thing is that the molecules of the water, they are striking with the Brownian particle, and then those molecules, they are definitely governed by the classical mechanics, okay, to good approximation, okay, and so there is a deterministic element in it, correct? So it's not completely random thing. I mean, the molecule is striking. If it is elastic scattering, it is going to some direction. That direction depends upon the initial angular linear momentum of the molecule, at which angle which strikes the Brownian particle. So underlying mechanics is deterministic. So it is not good to say complete randomness. At some cross-grained scale, the randomness comes, but basically the things are deterministic. Okay, the memory has to be there. So simple Langevin theory, we took friction as m minus m gamma because irrespective of the history of the particle. So what one does is that in the generalized Langevin equation, you put a friction coefficient which is dependent on time. So this is u t dash, velocity at t dash. T dash is very past, long past, minus infinity. So at past time t dash velocity, then this coefficient here, which is mt minus t dash, integrate over t dash up to t, minus infinity to t. So this is at the t is the present time. So all the past, effectively all the past information is captured by the memory. If you put m to be a delta function, it goes back to Langevin equation. So this guy actually captures the history, and it is sensible because things are not completely random. There is a deterministic evolution at the ground, at that microscopic substratum, and then it has to have this thing. Okay, then there is a random part which is there, and the external driving force is okay. This you can again do the same procedure. Fourier Laplace is called half Fourier transform. Why? Because it is basically minus infinity to plus infinity. It is written 0 to infinity because your mt for negative t is 0, because you can't have memory of a future like that. This is a half Fourier transform written in the square brackets. So this is the memory function basically. Now this question can be solved, it put like this. Now you can compare this equation, this is the Dute equation again, with a friction which is frequency dependent, with the old one which Dute derived in the turn of the last century. So this equation, this is the same equation. This is 1 by tau here, the iota omega is there, 1 by tau is there, but there it is not 1 by tau, it is actually m omega. M omega is 1 by tau omega basically. Okay, okay. So this is a very interesting function, and it has a lot of information in it. Okay, now, yeah. So now you put delta function, memory, and then it goes back. Okay. So, okay, I'm sorry, this is a very brief introduction to memory function formalism. There is more rigorous ways to drive it. So, because of the time constraint, I am not going into that. Okay, but
your answers have randomness introduced to R of t.
Randomness to?
Your Langevin equation has a R of t.
Yes.
But if the final answer of the conductivity it is not accurate.
Because you take ensemble average. It's ensembled over the randomness.
So it does not depend.
No, no.
What kind of randomness I take.
So when you take the average over the ensembles, that randomness gives you some sort of emergent behavior which is predictable.
So why to introduce that first place?
Now that is the microscopic description. That's the microscopic description. The Brownian particle, if you see, it shows the random motion. But then if you ask the question, what will be the average root mean square distance? What is the average distance of the Brownian particle from initial point? Average value. So you take 100 setups, 100 Brownian particles, and then you measure their distance away from the origin, because they will wander around the origin because there is no directed motion. But definitely they won't stay at the origin. It's like a drunk, the person who is drunk and then he is trying to move. He is not moving in any direction. Just if he is too drunk, like. So this fellow will not go anywhere. But if you take 100 drunkards and then basically their average behavior, you will see that on the average they are 3 meters away from their original position. Maybe after 1 hour they are maybe 3 meters away.
But ensemble average won't affect the memory term. It should also affect the memory term, right? Because in some sense it's at the microscopic scale. Because if my scale is larger,
yeah, it is average. This m omega, basically this m omega is averaged. It's ensemble averaged function now. It's ensemble averaged. Yes, it is ensemble averaged. It's ensemble averaged.
just T average.
It is ensemble averaged. It is ensemble averaged. I mean that you can see. For example, the problem which we give to students in an interview, the droplet is falling, okay, and then it has a constant 6 pi eta v friction coefficient, Stokes law. When the droplet is very small, then it starts with the Brownian motion. But at one point, the Brownian motion converts to systematic motion. So somehow that motion itself averages. There is a self-averaging that happens, isn't it? So although the fluctuations are there, when you take the average behavior, you can say the memory is now is a transport coefficient. Basically, it's a transport coefficient, which is well defined actually. It has a value. Although it is coming due to the fluctuations, underlying nature is the fluctuations, but the average behavior is described. That's what is relevant for our purposes, average behavior. Okay, now, okay, so basically this is one way to put the Dude formula in this form. This is called generalized Dude formula. Another is the Zhuanjing-Muri projection operator technique. Okay, so this is the Kubo formula. This is like a partition function. Like, for example, in equilibrium statistical mechanics, you calculate the partition function. Then from the partition function, you calculate the Helmholtz free energy. You can calculate pressure. You can calculate magnetization. You can calculate every quantity. Similarly, in non-equilibrium statistical mechanics, the correlation function is everything. So you know the correlation function? Yeah. Yeah. T-linear behavior resistivity. That's what I am coming to. It describes. Yeah, it describes.
What is the advantage of using Mori function?
Okay, I will come to that. It has some advantages, some disadvantages. It has. I will come to that. Now the question is that, okay, so this is the transport coefficient. This is very general. People use. This is applicable. Has been tested definitely for condensed matter systems. Even for quark-gluon plasma, people calculate the viscosity of quark-gluon plasma by considering appropriate correlation function. This is true in cosmology. This is true in high energy physics. This is true in condensed matter physics, statistical mechanics. Everywhere this is true. This is very, very fundamental equation. Okay, and this can be derived actually by rigorous perturbation theory, starting from the quantum mechanics. So I don't have the time. I mean, any standard book will derive this expression. Now, to intuitively, to just motivate it to you intuitively, how it works? It works that the fluctuation has a hidden information regarding the transport coefficients of the system. For example, let us say that you have you take water and then you throw some stone into it. It reaches some drift velocity, and then you take honey. In the honey, the stone will fall very slow, right? The thing is that because it has more viscosity, now the point is that if you spontaneously create some fluctuation, let us say that you have a water bottle, and by chance one region of it becomes hot, another becomes cold, spontaneously. I mean, I'm talking about fluctuations. I'm not talking about macroscopic flow of energy by violating the second law of thermodynamics. A fluctuation of energy happened, some part becomes hot, another being cold. Then immediately afterwards, the heat will flow from the cold region to the hotter region to the colder region. It will equilibrates. Now the way the system equilibrates actually tell us the dissipative character of the system. You see, that's the regression hypothesis. So for example, if you take a resistance, this is a resistance R at temperature T. Okay. Now if you take a very sensitive voltmeter, I mean you take a nanovoltmeter, and the voltmeter which can measure voltage in the nano, not even micro, nano. So this resistance will show a fluctuating voltage across it, because electrons are fluctuating randomly, right? So the voltage is proportional to the, if it is a 100 ohm resistance, then it is less voltage. If it is 1000 ohm resistance, it has more voltage. Okay, so basically the current fluctuations actually in the system, the current fluctuations and their decay. So in a resistance of 1000 ohm, the current fluctuation decay fast because more resistivity. So if you ask the question otherwise, if I can study the characteristic of the decay of the fluctuation of the current, can I tell something about the dissipative property? That's the essence of Kubo formula. So the character of the decay of the fluctuations tell what kind of dissipative property the system has. It's very far-reaching consequence. Actually, it was pointed out by Onsager, who got the Nobel Prize in chemistry. Onsager hypothesis, regression hypothesis, but it can be very beautifully put in a formal footing by Kubo using quantum statistical mechanics. Okay, this I want to leave it because you can do some projection operators, and then this formula can be written down in terms of the Langevin equation type. There are projection operators, we can skip this formalism. Now, yeah, so now 1972, Gorge and Wolfley, because this formula is very beautiful, formal, and it's quite pleasing to the eye, but how do you do computation with it, right? something, if you can do computation with, then only things is useful. This way, and this is the expression for the memory function. It has this projection operator L, projection operator Q. This is the complex frequency. This is another the Liouville operator, and there is no way you can do a computation out of it. Okay. So this Gorgy-Wolfe came up in 1972 with a more practical approach to computation of the memory function. So they express the memory function in terms of the current correlation function. This is the current correlation function expressed in this way. Okay. And then they argued that if the system path coupling is weak, there is a perturbative approximation of the memory function can be achieved. So they did that perturbative approximation. Okay. It is 1972, and this calculation details I have also sort of given during the coursework, and then I also written down in my book also in detail. Okay, let's leave this. So basically you can write the memory function in terms of this double angle bracket CC. C is nothing but the commutator of the current operator with the Hamiltonian. Okay, let's take the example of electrons and phonons. So this is the free electron part, this is the electron phonon part. So this is the electron phonon Hamiltonian. So you annihilate the electron in K dash state, create the electron in K state, and then it absorbs a phonon of a vector K minus K prime plus Hermitian conjugate of that. Now only assumption that undergoes this approximation is that this electron phonon Hamiltonian magnitude is much less than the free electron Hamiltonian. That's reasonable. The energy scale of the free electron Hamiltonian is electron volt in free good metals. Okay. The electron phonon coupling is milli electron volt. So this is the order of 10 to the power 4. I mean, the very good approximation. This works through as it is shown. Now, yeah. So basically, then what happens? You can plug these numbers. These are lengthy calculations. It's not difficult to learn. So the point is that you do get imaginary part of the memory function, which is the scattering rate. At high temperature, it is T linear. At low temperature, it is T to the power 5. The same result which you obtain from the Boltzmann equation, you can get it. Okay, it goes beyond the block Boltzmann equation. You can get this. The AC scattering rate, which shows the saturation, the base scale saturation, and it also shows Holstein mechanism. It is inbuilt into it. So it's the power of the memory function formalism. It has this Holstein mechanism also into it. So okay, so this is collected in my book which I wrote a decade ago. So all these details are there. Anybody can look into it. But there are many books out there. One is Zeeman's books, Electrons and Phonon by Zeeman. That's a big book. Another is G.D. Mahan, Green's function methods. It has very good discussion on transport properties also. Okay. Okay, but the memory function, I think the Gorgy-Wolfe, as far as I know, that I have covered in this. Otherwise, it is there in their PRB papers, but I have given more steps and all details I have collected. Anybody who students actually want to learn, can learn this formalism. It's very powerful, very helpful, and if you are interested. Okay, let's shift gears.
What happens to Strongly coupled system?
Yeah, strongly coupled systems, it doesn't work.
This will not apply like
No, it won't work. It won't work.
Then what happens?
Okay, so what happens in this formalism, basically when you deal with the, because I have not gone into the details of the computation, so basically you will have current operators sitting here, and this current operator will have e to the power minus I upon h bar h0 plus h electron phonon times t e to the power, let's say this is 0 time t equal to 0 e to the power plus I upon h bar h0 plus electron phonon part times t. So this is the Heisenberg operator which appears in the commutator. So what they argue that Gorgy-Wolfe, they just throw away the electron, because then this is a known, because this is nothing but epsilon 0, and they take the average with respect to the canonical ensemble, this becomes epsilon 0, integrals can be done easily. But this is approximation. Now if you are saying that how do I do if I have strongly correlated system, then because the question is that I don't know how to diagonalize the full Hamiltonian. This is good when you have weakly coupled system and the H0 spectrum is known to you, free electrons.
Like the memory function, there's another similar method called memory matrix.
Memory matrix, right?
Which is by Froster and company. Froster has a thick book.
Yes, Froster's book, yeah.
I
forgot to tell
I
you.
don't know. I don't think it's in the library.
It's the same stuff.
No. There is a difference because Froster's thing goes.
No, hydrodynamics. That's applied to hydrodynamics.
But the approach goes over to the strongly coupled. So I came across this reading Raghu Mahajan's paper on some CFT
They
do exactly the same thing but now for strongly coupled.
Yeah, I agree with you because this formula. Definitely.
There is an extension.
This formula is exact. There is no approximation. This is exact. Now, maybe they have developed methods to deal directly with it.
They have a particular way of dealing with this for the strongly coupled.
I see. Yeah, maybe they have developed methods to directly deal with it. This is exact formula, but these guys, this Gorgi and Wolfley, which is because they argued that in condensed matter systems you will always have coupling with this scattering degree student which is weak, like electron phonon impurity scattering, electron phonon scattering, electron magnon scattering. All those are weak couplings. So under that it works.
Another advantage which I don't guess from the papers is that memory function at JJ is the correlate.
Correct.
They can have J rho, all kind of possibilities.
How? That is why I just gave one example. I mean, you can have.
They usually say, their paper says that you can be extended to arbitrary set of correlators and also to strong.
Okay, I will look into it.
I don't think that book is there in the library.
Yeah, I will look into it, and I will show you quantitatively why we should believe in that. Okay, so switching gears, this is the problem of Cuprate superconductivity. So Cuprates are notoriously difficult to understand. Systems are 35 years over has gone. People don't understand what mechanism. Zero doping, it is antiferromagnet. When you start dope, antiferromagnet goes away, the superconductivity emerges. Now exactly at this point P star where the superconductivity is maximum, there the resistivity becomes density linear. It is density linear. This is a cuprate. This is a typical metal. What happens? If you take a typical metal, you will see that at room temperature it is T linear. At low temperature it starts to bend. People have done experiments going up to millikelvin. They see complete T linear behavior. It's completely some fundamental scaling law is going on. Then people have coined the word Planckian dissipation. Okay, anyway, so
how far does the T linear go?
it goes up to 800 Kelvin, millikelvin to 800 Kelvin, really at very hot temperatures, all T linear.
Without any pressure.
Okay, this without any pressure, this is quantum critical point.
No.
Here no pressure.
800 Kelvin
Is like 600 degrees centigrade, something like that, very hot.
500 degrees.
Yeah. So something really novel happening. But this T linear is not only seen in cuprate, it is seen in iron-based superconductors. This is the example of iron-based superconductor. So at doping of 0.1, same phase diagram, similar phase diagram true for iron-based superconductors also. It is T linear at that, rest becomes different from T linear. Then there are this is for cuprates, it is T linear for cuprate at that doping point for the quantum critical point. Then there are organic materials where you have organic molecules, quasi-linear chains at a particular critical pressure, it's become T linear. There also heavy fermion systems where you have Kondo lattice, there is a conduction electrons and then there is a localized electron, there is a Kondo coupling. That also the critical doping, the resistivity becomes T linear. So at one particular point, which is called quantum critical point. Quantum critical point, why? Because this critical point is at zero temperature. This is the temperature, this is zero temperature. So somehow they are magnetic systems. It's antiferromagnet, but when you dope, it destroys. The magnetism is not completely destroyed. The magnetism resides at a short length scale. But at P star, something happens to magnetism. Maybe there are long range fluctuations. Okay, and it's why this phenomenon is very, very important is that because it's not a property of one material. There in cuprate there are hundreds of materials show this. Then in heavy fermium hundreds of materials show this. So this means that it's a universal law.
He is doping.
Huh?
He in the previous picture is doping.
Is doping, yeah, is doping. So this means that the P linear is a universe. That's what it is believed, that it is a universal phenomenon. It has universal explanation. Okay, that's the question. Now, so okay, I mean, to deal with cuprates, one has to have what is the fundamental model, and this has been a very difficult and debatable area. Was a Nobel laureate, people definitely believed him, but at the same time, in the same time when he advanced his resonant valence bond theory based on the one-band Hubbard model, V.J. Emery developed three-band Hubbard model. He argued differently from Anderson. He said that Anderson said that you look at copper spins. Okay, so this is the kinetic energy. This should be equal sign. Kinetic energy of the particles in the copper, and then there is a strong Hubbard repulsion on copper. When they put two electrons on one copper side, it's called Hubbard U. Okay, it's a simple model. Okay, but Emery argued that this simplicity is good, but you are oversimplifying the problem. You are actually throwing the baby with the bathwater. That's what he said. When you're throwing too much. I mean, in physics we simplify a problem, but you don't simplify too much. I mean, this is a paper I have written very recently, submitted, and it's generating some interest. It's still contentious, basically, but there is a sizable community now in condensed matter physics, which is more towards Emery, and then it says that he argued that when you dope the material, so doping creates holes which are mobile on oxygen sublattice. The copper spins stay, because copper spins are antiferromagnetically correlated. Once the holes are there in oxygen sublattice, this antiferromagnetism weakens because the superexchange weakens. There are spin fluctuations on the copper sublattice, but the mobile carriers are on the oxygen sublattice. So if you look at this, there is a copper, oxygen, copper, oxygen, copper, oxygen. So what we did is we took a model, simple two-band model, where the copper spins are sort of a platform for paramagnons, and oxygen sites contain mobile electrons. Now the two components.
The spins are pinned. In some sense.
They are pinned, yeah, because of Hubbard U. They are pinned on the copper, but they can fluctuate. Okay, with this model. Which one? Paramagnon, yes. Okay, there are lots of papers, like for example what I have quoted in the paper. So in one paper they say that there are paramagnon excitations seen with the resonant inelastic scattering experiments right in this. So they say the paramagnons exist throughout. There are all paramagnons exist there. There are lots of, not just one paper, one nature physics paper I am quoting. There are many papers which say the paramagnons. Okay, first, for example, in a classical magnet like iron, so you will get paramagnons above the Curie temperature, below you will get magnons, okay, and nice arrangement. But now there is no classical phase transition, it's a quantum phase transition. So very down to low temperature, I mean at absolute zero people cannot go definitely. Millikelvin, yes, they go. Okay, so the paramagnons are like, okay, yeah, I mean like, so for example you have this antiferromagnet arrangement, nice antiferromagnet arrangement. So this guy you flip, this guy is flip upper, otherwise, so some wave is generated, and so some wave of magnetic fluctuation is generated in the lattice. But yeah, I am coming to that. Yeah, so but in a paramagnon, so the thing is that there is no long range order above the Curie temperature, but short range magnetic fluctuation exists. So these paramagnons guys, they live only a very small region of space. So some magnetic fluctuation happens on a length scale, which is the correlation length scale, but they are not long propagating. That's the standard definition, and the dispersion is linear. That has been measured by neutron scattering also, as well as this experiment. The paramagnon dispersion they see is given by some stiffness constant times the wave vector. Q mod. This is the dispersion of the paramagnons which they have seen.
Paramagnons are like on top of the main paramegnons. You need an yield job.
Yeah. So
at P star, when C is
Yeah.
close to P star, you have already lost the yield on.
that's the whole problem. The point is that nobody understood what is pseudogap. What happens that what they do know is that in this region up at the room temperature up to 5 lattice sites, one lattice site is 4 angstrom. Up to 20 angstrom, that length scale, the spins are correlated. Then they become uncorrelated. Then another patch. Okay, this is C. But since there is no Curie temperature, basically there is no sharp magnetic transition. So these fluctuations exist, magnetic fluctuations exist throughout the phase diagram. But once you go below this point here, then those guys, then there is a long range antiferromagnetic order, infinitely long range antiferromagnetic order, then those fluctuations doesn't exist, but you now have long range antiferromagnetic order. So you can think of magnons then in this region. But we are far away from the magnetic region. It doesn't mean it's that's the whole trouble people have been fighting for cuprates, because it's not a Fermi liquid. It is not a magnet. It is a Fermi liquid with lots of magnetic fluctuations. How do you deal with this problem? How do you deal with this problem? So that is why.
Describe these somewhat shorter range correlations.
Yeah, neutron scattering do see correlation length.
But if you are saying that these are not really the long range ones,
Not long range.
then it essentially means that whatever the exchange is happening, paramagnon or whatever, it has developed a large mass.
How do I understand that? Large mass.
Large mass will mean shorter range for the potential, the usual non-reducing.
Yeah, we can think of that way
There is
also.
a mechanism, maybe some non-perturbative thing. Nothing is happening. This is probably not perturbative.
Yeah, it's not okay. Let me come to that. I agree with you. How we handle this problem? Let me first complete that. Then I am going to come. This is a very serious question. I am going to come to that. We did it traditional way. Surface is working. Okay. So this is the Hamiltonian we took. Electrons, paramagnon part, electron-paramagnon. So these are free electrons, and this is paramagnons, boson with some omega q frequency, and this is electron-paramagnon, just like that electron-phonon matrix element. But here is the MKK prime, which is the paramagnon matrix element. That's something very special about it. Okay. Then this is the memory function. C is given by the commutator of Ix with the H. Okay. The current will commute with the free electron part, current will commute with the free magnon part, paramagnon part, current will not commute with the electron-magnon part, and there is an expression for C. So you plug these expressions of C here, do some mathematics, simplification, you get this expression. Okay, and then you can simplify this KK minus prime, you introduce a delta function, introduce this delta function 0 to some, there is a delta function 0 to infinity dq, with this delta q minus k prime. Now just say that k is pointing in the z direction, k dash is making an angle theta with that, and then d theta is the angle. You do this integration very easily. I mean the theta function of a function can be easily calculated. Okay, this is not very difficult but cumbersome. Okay, it takes time, maybe 20 pages calculation. You will get this memory function. Okay. Now comes the important part. Here we introduce a legitimate upper cutoff to the paramagnon wave vector. So what I did is I just introduced this dq. dq is the wave vector which is equal to the change in the wave vector of k minus k prime. The electron goes from k to k prime. The momentum must conserve. The q is the wave vector of the magnon. But this is 0 to infinity. So what I did, I cut off that. I just put q cut. It cannot be infinity. Okay, the field theory it can be infinity. But since we are dealing with condensed matter systems, it has a finite lattice. So this q cut is pi by a. A is the lattice constant. The most shortest possible distance conceivable in 2D lattice. This but now this is guy is sitting here. This is the matrix element of the electron paramagnon scattering, and this we did in 2D. And this is the imaginary part of the memory function. This is the scattering rate. Now what happens that if you take this m as constant, this is traditional way. this is the problem given to the student. If M is constant, 3D metal or even 2D metal, magnetic metal in the paramagnetic state, what should be the resistivity? Okay, and then you see that regular electron-magnon coupling, constant matrix element. In the case of a magnetic metal in the paramagnetic state, electron-paramagnon coupling matrix element is taken as constant, Q independent. You can take M square. There is no Q, MQ. I take M out. This integral is simply handled. So if you have antiferromagnetic case, the magnonic dispersion is Q linear, but if you have ferromagnetic case, in the ferromagnet, the magnons goes as Q square. Magnons goes as Q square. And the high temperature limit is T linear. You can take the high temperature limit. High temperature limit, it can be very easily simplified. And the low temperature limit, you can just put beta omega Q as X. You can simplify this thing. And you do get, I mean, this is a known result that in the case of ferromagnet, the resistivity, low temperature resistivity T to the power 3 by 2. Like in phonon case, T to the power 5, but it is T to the power 3 by 2 when there is a electron-paramagnon state. This is a known result basically. So the theory is derived, but these results are experimentally known. Now comes the crucial question. So this problem I was thinking on one weekend, and then I was asking the reverse question. So I thought that if I get at low temperature not TQ, I should not get TQ, or I should because the TQ was coming because Q square was sitting here. That's how I thought about it. This guy Q square, TQ Q square. If I can get rid of this Q square, I will not get T to the power 3 law at low temperature. How do I get rid of it? Then I thought, why don't M can be inversely proportional to Q square? Okay, so I just thought of this. Then I search in the internet. Yes, this kind of matrix element does exist, and this matrix element is true for a system near a quantum critical point. Okay, so the square of the electron-paramagnon matrix element square goes 1 by Q square. This is a correlation length square. Okay, so that gives me confidence. I just plug this guy into that equation. So I plug it.
M of Q or
Chi of
is the vertex.
Is the vertex.
Paramagnon vertex. So
Okay.
it has a Lorentzian form.
Yes, it is a Lorentzian. That's the most beautiful thing. In Cuprates, near the quantum critical point, is Z equal to 1 scaling, because Lorentz invariant. It becomes Dirac physics comes into picture. Suddenly it comes into picture. But why? That is still open problem. I was asking you that we should have a concrete model where we can show, okay, the coupling of the electrons with paramagnons is given by the susceptibility, right? Susceptibility. Can we calculate susceptibility of a 2D lattice with spin fluctuations and show that susceptibility at this Lorentzian form? That's the problem we have to solve. Okay.
It's just the vertex.
This is just the vertex. You have to multiply it by boson.
Some constant. Okay, that is just constant.
Boson property. That is the
So this is a non-local vertex.
That's what I was asking. This is a non-local interaction.
Okay.
Not local.
Let me make it clear. The physics of this I still don't understand. I'm still struggling now. I think we can sit together and discuss it. Physics is not clear to me why this matrix element arises. But I saw that the same matrix element originated in very tough calculations of Abanov and Chubukov.
No, Abanov and Chubukov assume that the vertex is a constant and the boson propagator has
Okay.
Lorentzian form.
I am not I have to read his paper. We can sit together and read together. But they come to this conclusion.
No, so
They come to this conclusion.
no. So if this is the vertex, then one is definitely dealing with a non-local field.
Yeah, I'm coming to come to that. I'm going to come to that. I'm coming to that.
Even before one does anything to do with Cuprates or anything, this theory will have its own problems. Non-local theories have their own problems.
Because you see, at this P star, what happens that you have magnetic fluctuation going on. Now suddenly this P star, okay, maybe someday I will give another talk. This P star has host of very abnormal, unusual properties. Okay, it may happen that near P star there is a long range correlations extended
No,
infinity.
I mean, the long range correlation does not necessarily mean that theory itself, the Hamiltonian itself is long range.
It turns out like that. Actually, how it turns out we don't understand.
So one thing is the following. In many cases, even in field theory, sometimes what is done is there are two notions of what is called an effective action or effective Lagrangian. One is Wilsonian, which is purely local. It cannot be non-local. The other is what is usually called 1 pi or the so 1 pi. What they do is so Wilsonian. What happens is you integrate out modes. So if you are at this scale, lower scale,
higher energy integrate.
Higher modes.
Higher modes. You got a lower modes left.
For the 1 pi or the traditional effective action, you even integrate out the 0 degree, the 0 momentum or 0 energy.
No, that you don't. Then nothing will be left. No.
You get that?
No.
You get that?
No. You don't. See, how do you look? Okay. How do you look?
Integrate out 1 over k square on those modes, you get that.
Okay. So you have some magnetic spins fluctuating, right? Okay. So this is some mode is there. I'm just one mode I plot with wavelength lambda. Okay. Some 2 pi. I mean this goes as 1 by q. Okay. Now how does so this is happening on a copper sub-lattice. This long wavelength modes are there on copper sub-lattice where the spins are there. Now there is a conduction electron. The conduction electron is a spin. Okay, and it goes from state K and it goes to K dash. It scatters.
Yes.
Okay. Now this guy couples. Just a second. So the coupling is dipole moment, dipole coupling, and this coupling diverges when this is a very long range. It diverges this coupling. So that's why this Q divergence is there. You put Q equal to 0 means infinitely long wavelength, and this guy diverges.
No, but how do you write out? See, this is
okay.
really want.
No,
How do you write
I
down
need
a
to
Lagrangian or a Hamiltonian or even a
to tell the truth.
model for it? Lattice is-
See, qualitatively I understood it, but I need to do rigorous derivation of this. Let us
So
put
right,
it.
at
I just took it.
At this point, it is an ansatz for us.
It is ansatz for us. Okay, let's be satisfied with it. But this expression is derived by Chubukov in these two references. This same expression is derived by him. Okay, but
the integrand is the same, the vertex and the propagator.
we will see through it. Let us say this is ansatz. Assume it. And then I discussed this with another person, Professor Henri Tremblay. So he also said yes, they also drive this in the context of quantum critical matter. He showed me a reference. Next page there is a reference there, and he also showed that this IT should go as 1 by t. There is another ansatz which I will do, and they have derived it, but I don't understand their work. Maybe we can sit together and understand. Okay, but this is ansatz. Now what I did, so this is the take m inside back, m square inside back. You put this this m square there, and you simplify. You get this expression. You just put beta h over omega q as x, then simplify. You get sitting something in the here. Now you see. So then I ask the question. I get cavity here, right? If my temperature is low as compared to d1 q cot, d1 q cot is a Debye equivalent of Debye scale. If my temperature is low, then I can push this limit to infinity. Then this is just a constant, but the t is sitting. T was not leaving me actually. It was sitting here because you get perfect. You see, I mean, you have this perfect linear behavior, right? The perfect linear behavior. So perfect linear behavior will not come until as your correlation length is sitting. So then I ask that the correlation length should be d by kVt. The correlation should diverge with the time temperature, and I just plug it back. I get d1 by d. So this entire and then this limit I push to infinity. You see, kVt times this integral. This is the Planckian law. The Planckian law, they argue this. From last 20 years, they are saying that this m double prime t, which is 1 by tau, is given by kVt, okay, alpha times kVt divided by h1. Now I have the expression for alpha is order of 1, and this alpha is depending upon d1 by d. Okay, so somehow this ansatz and this ansatz leads to an expression of scattering rate which is temperature linear. Okay, let us actually look into numbers basically if we are to really do the justice. Okay, so then I look into the literature for LSCO at undoped this D1. The D1 is this how the D1 is the value of the how this the spin, the dispersion. So where I did write this dispersion? Yeah. So H bar omega q is D1, D2 is for ferromagnet, leave the ferromagnet, D1 is for antiferromagnet, D1. So D1 value, okay, I took this, and then also I see a theoretical model, Heisenberg model, 2D antiferromagnet Heisenberg model. So by putting the legitimate value of J and all those things, then this value of this upper cutoff comes out to be really large, 5000 Kelvin. The debase scale here is 5000 Kelvin. You are measuring resistivity up to 800 Kelvin. Okay, so it is actually linear, but then it was saturating. Okay, then I was searching the literature for BCO. Then I came up with another risk experiment. They say that the paramagnon energy scale as large as 300 millielectron is reported. This is a Nature Physics paper. They report this with risk experiment. 300 millielectron volt. Then I plug this number, which is perfectly linear. You see, it's perfectly linear. Okay. In conclusion, the following points I want to make: linear resistivity Cuprates originated from scattering of mobile carriers on oxygen sub-lattice by generation of paramagnons on the fluctuating spins on copper sub-lattice. T20 perfectly linear behavior attributed to quantum critical point deep inside the superconducting dome, and the magnetic correlation length. Our theory demands this. Okay, so we have been sort of discussing this issue with the Tremblay.